looking at review problems for chapter 4 rather. Number 1. Is it possible for an object to be in motion if no net force is acting upon it? The answer is yes. The object could be moving at constant velocity. Examples. If your car is moving down the highway with cruise control on, what that means is the forward forces are balanced out with the backward forces. In addition, the up forces and down forces would also be equal to one another. So you could be moving with constant velocity, or the singular example of something out in space. If you are an astronaut and you throw something, a ball or a wrench, out into space, that object will continue to move with a constant velocity until acted upon by an outside force due to Newton's first law. Number 2. If an object is at rest, can we conclude that no forces are acting on it? No. We can conclude that no net force acts upon it. We can conclude that the forces acting on it are equaled out, and therefore nothing is making it accelerate. Number 8. A chair is pushed with a force of 185 newtons. You got force of gravity is 155, and the force of the floor is 155. So what you'll have here is you'll have a chair shape, because we're drawing a free body diagram. So here's my chair. And then after you draw your chair, you're going to have 3 arrows, because the only reason you don't have more is they only list 3 forces to work with. So I'm going to have, for say, my down arrow for the force of gravity, my up arrow that we would later learn is called normal force, and the pushing arrow that they gave you. And you would label it force of gravity 155, normal force 155, and a pushing force 185. And then number 9, it says draw a free body diagram of each of these things. So basically, these are pretty simple. You got a ball falling in air resistance. So you have a ball, and in the presence of air resistance, you're going to have, in the presence of air resistance, you're going to have, it's falling, so air resistance is going backwards, gravity is working down. And then you're going to have a helicopter. Same basic thing. You know, it's just, now it's a helicopter, right? You can put the landing gear on it. Now it's a helicopter. Here, there's a propeller. You've got the force of the thrust, the lifting force on the helicopter, and force of gravity. And then an athlete running along a horizontal track. Here you'd have your person, and you'd have, just add a backward force to it, you'd have gravity in the track pushing up, you'd have the forces propelling the runner forward, and resistance forces acting backwards. And you just label them as such, and there is your diagram. In number 10, 4 forces act on this hot air balloon. Well, looking at the forces, because it's not a box on the ground, things do not have to be equal, and they aren't. And you look here, you've got vertically 5,120 newtons up and 4,050 newtons down. And if you just subtract the difference between those, you'll notice that there is a net force of 1,070 newtons up. And then you'll also notice when you look left and right, you've got 950 to the right and 1520 to the left. And you'll subtract, and there's a difference of 570 to the left. And when we have a shape like this, we need to find the net force acting on it. And overall, the hot air balloon would be going to the up and left. Now, when we draw vectors, we don't draw them tail to tail, we draw them nose to tail. So this 570 down here, I'm going to draw like that. And then you can see you have a number and a question mark. So you can use Pythagorean theorem. A squared plus b squared equals c squared. Then you have number 12. A dog pulls with a force of 5 newtons at 37 degrees. So 5 newtons at 37 degrees. Find x and find y. And it's just a matter of doing SOHCAHTOA. Hypotenuse, angle. So cosine of the angle times the hypotenuse gives you x. Sine of the angle with the hypotenuse gives you y. And it ends up being a 5, 4, 3 triangle. And then we have number 15. An astronaut is on the moon. He has a 110 kilogram crate and a 230 kilogram crate. How do the forces required to lift the crate straight up on the moon compare to the forces on Earth? Well, on the moon it would be easier. There would be less force because the gravity is less. At the same time, if you want to compare the two crates against each other, the heavy one's still going to be heavier on the moon. And I'll do number 23 here also before ending the video. 23 and 24 I'll do here. Number 23, explain the relationship between mass and weight. Well, that goes right with the astronaut question. Mass is fundamental to matter. All matter has mass. Mass is a measurement of how much matter you have. Weight, on the other hand, is the force of gravity acting on something. If you go to a place with a different gravitational field, you will have a different force of gravity. So the Earth and Moon, for example. On Earth, the acceleration of gravity is 9.81. On the Moon, it's 1.6. On the Moon, you have roughly 1/6 the weight as you do on Earth. But you would have the same mass on either place. So that's the difference. Weight is the force of gravity. If there's no force, there's no weight. That's why astronauts are considered weightless up at the International Space Station. And that's that. So that moves us to number 24. When you throw a ball up in the air, what force is acting on the ball halfway up, and what's the force on the ball at the top? As soon as you throw a ball, if there's no air resistance, as mentioned in the question, what force is acting on the ball? Well, just gravity. That's the only force acting on it. If that is the only force acting on it, that means that that's the only force you can calculate. So 0.15 kilograms times g. So your answer comes out to 1.47 for both A and B because gravity is the only force acting on it.